Thank you very much. I want to thank the organizers for the invitation and all the participants for this wonderful workshop. It's great that we still have another half of it, so it's been very good so far. Today I'm going to talk about the loop race random walk in 3 dimensions. So this is based in a joint work with Xinyi in Peking University and Daisuke Shiraishi in Kyoto University. So the Minkowski content will appear by the end of the talk, and really what we are going to talk all along are 1-point function estimates for the loop race random walk. And in particular, we are going to look to the case in 3 dimensions. So let's start just with the definition. It's very simple, and probably most of you are already familiar with the model. So we are going to work on set D, and we have our beloved simple random walk. So we are going to stop this simple random walk when it exits a ball of radius m. So I'm going to denote my balls, the unit ball by d, and this indicates that I'm looking at the ball of radius m. So we have our simple random walk, and it's evolving, and it doesn't have any constraints, but then we stop. Sorry. So the loop erasure simply erases all the loops as they appear chronologically. So we see that this is a first loop, and then it goes this way, and then, well, it backtracks. So we also erase this part. And essentially, we're taking, from the origin, we take our last exit edge, and then we get to the next vertex and take the last exit edge. In this case, we only got one, and so on and so forth. So we obtain a simple path between the origin and someone on the discrete boundary of the walk. So for this loop erasure of the simple random walk is a loop race random walk, and I'm going to denote by gamma m to indicate that it reached some Euclidean distance m. So this is a model proposed by Greg Lawler back in the 80s. And as many of you know, the original motivation was to have a simple model to understand the self-avoiding random walk. It turns out that it wasn't helpful for that, but, well, thanks to the efforts of a lot of people, particularly of Greg Lawler since the 80s, it turns out to be an excellent model to understand criticality. And, well, several people in this room have contributed to the understanding of the loop race random walk. So let's start. Let me show you what is going to be our framework. So instead of looking at a ball of radius m, we prefer to fix the ball of radius 1, so this is d, and the scaling will be on the lattice. So set d would be rescaled by some factor 1 over m. So it would be an equivalent description. Instead of taking a simple random walk that reaches distance m, we take simple random walks on this smaller lattice so that each step has length 1 over m and until it reaches Euclidean distance 1. So depending on the question that we are looking at, it is more convenient to look at it this way or the other. Since we are interested in the scaling limit, it's nice to fix our unit ball so all the curves live on the same compact space. In 2 dimensions, an actual simulation will look like this. And, well, there are several nice, and, well, they are quite simple, but I didn't make them simulations. These were made by one of my undergraduate students, Jorge Emiliano Alvarez Gil Leiva. We have very long names in Mexico. And, well, this would be in 2 dimensions. And I actually did this one a long time ago, and this would be one loop race random walk in 3 dimensions. We can, in 3 dimensions, we can think that if we have all the blue and the orange path, this would be the simple random walk, and we are just keeping the orange path. So, like, everything that is in blue are the loops that we would have erased. So, as I was telling you in the beginning of this talk, we are going to look at 1-point estimates, and this is the probability that a particular vertex, in this case, this would be taking 1 point on the unit ball and then take the closest point xn that actually belongs to the lattice. And how does the probability that this point xn belong to our loop race random walk on the lattice as set rescaled by 1 over n? And one of the nice consequences of having good estimates for the 1-point function is that this helps us to get growth exponents. This also helps us to actually get the scaling limits. And by the end of the talk, I want to show you how we can also get the Minkowski constant and why we care about these things. So this is the quantity, and having the estimates for this probability can be sometimes a little bit dry, but we have a lot of cool stuff coming out from them. And the point is to get the sharpest estimate as possible so we can have better results. So, it's very nice to have Rick over here because this is our, one of the first big results for growth exponents of loop race random walk. So in 2 dimensions, he proved that the growth exponent is 5 over 4. So in this case, I'm actually looking at the infinite loop race random walk, so I'm not rescaling the lattice. So we can actually think that we are comparing the Euclidean distance, so the size of this ball, with how many steps it takes the loop race random walk to reach that distance. So we can think that this is a game of intrinsic distance of the loop race random walk versus the Euclidean distance that it's on the underlying space. So we denote by mn the number of steps that was required. Maybe this should be an inequality. Let's say that to reach distance n. I'm sorry, this is not the best notation. What I want to say by mn is how many steps are necessary so that we can exit an Euclidean ball of radius n. And then we look at the expected value of this random quantity, mn. And if we take logarithms, what Rick proved is that this is of the same order of n to the beta 2. So this would be n to the beta 2 plus some correction in the exponent. And if you look at this, how do you get this? Well, this is actually from the 1-point function. So what Rick proved is that if you look at the probability that a given point belongs to the path of the loop race random walk in 2 dimensions, in this case, we can nicely write this point as in polar coordinates. This probability scales as the radius to the minus 3 over 4 and the correction in the exponent. So the growth exponent, this is just an expectation, so it's very easy to compute now once that you have the probability that a given point is in this loop race random walk path is the dimension minus, this should be 3 over 4. So 2 minus 3 over 4 is 5 over 4. I apologize, there was another typo here. But you can see that this is it's a very simple calculation since this is an expected value. So the difficult part is to actually get a good approximation to what is the order of the exponent of this 1-point function. So the next step is to understand the scaling limits of loop race random walks, and this is where the loop race random walk shines, because when Odette Schramm was looking at loop race random walk and uniform spanning trees, that's what led to the definition of the Schramm-Loewner evolution. And in the case of the loop race random walk, is the Schramm-Loewner evolution with parameter 2. So these are the dates where these results were appeared for the first time on the archive. So in this first paper, Odette Schramm proposed the scaling limit, and what was lacking was the proof of the conformal invariance, which was achieved and later a few years later in work of Greg Lawler, Odette Schramm, and Wendelin Werner. So in the 99 paper, the proof was assuming conformal invariance, then this is the scaling limit, and then in this joint work, they proved that the conformal invariance was true, so the Schramm-Lochner evolution of parameter 2 is the scaling limit of the loop-raised random walk in 2 dimensions. But you have to look at the topology. With respect, you have this weak convergence of the loss. So the strongest result in this sense is the convergence in the natural parameterization. So you actually want to think that your cubes are parameterized so that every time that you have a loop-raised random walk and you advance on each one of the edges, you go through these edges in the same time as any other edge. So, but you want to rescale that properly, and that's where things become, one needs to be more careful. So in 2016, Lawler and Biglund gave this proof of convergence of the loop-raised random walk in the natural parameterization, and the scaling limit would be parameterized by its Minkowski content. So in this paper of Greg Lawler and Scott Sheffield, they show what would be the correct way to parameterize the limiting object, without one can choose several ways to define a measure on the limiting object and say this is a parameterization. But the nice thing about this paper is that they actually prove that if you just assume domain Markov property, conformal invariance, maybe I'm forgetting something else, but essentially what it would be a good intrinsic measure, then the Minkowski content should be the answer. And this was, the existence of the Minkowski content for the Schramm-Lochner evolution as you change the parameter was proved later in another work by Greg Lawler and I believe one of his students, Resai. And the criterion that they use is based on one-point functions. So we are actually going to use the same criterion to show the existence of the Minkowski content in the 3-dimensional case. So the way that they show this, it uses techniques that are, actually used that we know what is the limit. But at the end of the day, the one-point functions and two-point functions give us a way to understand what would be, the existence of this Minkowski content, and then gives out these nice results where the convergence is what it should be. So as I told you, to show the existence of the Minkowski content, they needed a strong one-point estimates. So in this case, Benes, Lawler, and Biglund improved the one-point estimate of Rig, so that now it is actually, they understand very well what would be this constant in terms of the point that you are looking at, the probability that it belongs to the loop-raised random walk, and it is asymptotic equivalent to R2 minus 3/4. So this is kind of the goal, to have estimates of this type. So, this is a conference of statistical mechanics beyond 2D, so now we are going to go beyond 2D. But these two-dimensional results are kind of our benchmark. This is the, surely we can understand even more about the scaling limits, but for non-Gaussian behavior, this is as good as we can have so far.
Okay. So before the convergence with the parameterization, it was just the trace that converged?
There's this, so you, let's say, Lawler, Schramm, and Werner, they have this norm. Essentially, you define norms for comparing two paths. So in that, they use something that is called a norm for unparameterized paths. So essentially, you have two paths and you compare against their best parameterizations as they are close to each other. And the way that SLE would be parameterized is not by its Minkowski content, but by the half plane capacity. So, I mean, the natural way, given the construction of SLE with conformal functions. So the norm for unparameterized paths made sense because there is no reason to believe that the loop race random walk would converge to this other, I mean, conformal type parameterization. And then there was this question, well, what would be the right way to change that? So now in this later convergence is closer to what we look at and will appear later. Maybe between there were other norms, but I haven't checked that recently. Okay, so now we go beyond 2 dimensions. So here in the 2-dimensional case, the scaling limit is SLE, and we have this order for the 1-point function. So in dimensions 5 and above, the loop race random walk converges to Brownian motion, and the 1-point function is what you would expect if you converge to Brownian motion. So it's 2 minus the dimension less the simple random walk. 4 would be the upper critical dimension, so the scaling limit is still Brownian motion. You have to be a little bit more careful at the time that you prove the scaling limit because there are log corrections. And in this case, the 1-point function, I mean, it would be 2 minus the dimension. So the dimension here is 4, so you get minus 2 over here. But this log n to the minus 1/3. So in 3 dimensions, this is kind of the topic for today. And the scaling limit is what we are going to denote by K in honor to Gadi Cosma, who proved the existence of this scaling limit. And what we are going to also justify is that this 1-point function scales like n to the beta minus 3, where 3 is the dimension, and beta is actually, well, the growth exponent as it happened in the 2-dimensional case. So how's this story? So in this amazing breakthrough by Gadi Cosma, he proved convergence of the trace. That is this norm, this type of convergence that you have in mind. So in his framework, he had a polygon, and this is part of the construction. Like he modify, you are on set 3, and then he modifies set 3 in this complicated and very smart way, so that he can understand the scaling limit of the 3-dimensional loop race random walk. And then we fix this polygon and look at the renormalized lattice. Sorry, another typo here. No, this is right. So set 3 is renormalized by 1 over m. So gamma m would be the loop race random walk on this inside this polygon with rescaled lattice. So the theorem is that with respect to the Hausdorff metric, so the Hausdorff metric essentially compares shapes inside a compact subset. If we look at the shape of the loop race random walk, it converges to some limit. Here I'm breaking down the convergence along dyadic scales, but actually the convergence is along it's along the reals. So it's a full convergence, but with respect to the Hausdorff metric. And kind of, the convergence is like amazing, but what is also like great and amazing is that he proved that the scaling limit is a scale and rotation invariant. So the scale invariance is kind of by definition, because this is done by scalings. I mean, by construction, you get a scale invariance, but rotational invariance is very special. And we actually, in our work, we use it heavily. And it's not obvious that, it's something that you would expect, that when you go to the scaling limit, the limiting object should also be rotational invariant, but it's not obvious because if you think about it, the beginning object was actually on set 3, so it doesn't have all the symmetries of R3. So this is, I believe, one of the initial motivations, not only to show that there is an scaling limit, but to prove that it is rotational invariant. So the later work went to understand what would be this limiting object K, and one of the issues is that the only way that we get to access K is through the limit. We don't really have a description in terms of three-dimensional Brownian motion or some transformation of Brownian motion or some other like SPD. Like we only know that K is the limit of the three-dimensional loop race random walk. So Daisuke Shiraishi, one of the co-authors, and Artyom Sapochnikov proved that, as you would expect, the limiting object is a simple curve that starts in 0, where you began, and ends in the boundary. And Daisuke went to prove like several properties of this three-dimensional loop race random walk, and of course they were based on estimates that he got for the one-point function. So in his paper on the growth exponent for the three-dimensional loop race random walk, I'm using the bad definition again. Well, he proved that the one-point function, so the probability that a point on the grid of rescale by 1/n, this point xn, belongs to the loop race random walk in that rescale lattice, is scaling like n to the beta minus 3 plus some correction on the exponent. So similar to Rick's result for the two-dimensional loop race random walk. And with that, he got the existence for, well, with that and additional work, like for additional work for these two results, he gets that, well, this beta is the growth exponent for the three-dimensional loop race random walk, and also the Hausdorff dimension. Here, we know that beta is between 1 and 5/3. These are bounds that Greg Lawler gave even before the proof of the existence of this growth exponent. So you can see that, I mean, at least is non-trivial, so this is strictly larger than 1, but the upper bound is like far away from 1, it's 5/3. At least it's strictly smaller than 2, so this is not Brownian motion, it's a different exponent. And there is no reason to expect that beta is a nice rational number, so there are simulations by David Wilson that show that it seems that if you want to approximate beta with numerical methods, it's just some irrational number that exists. But that's fine. There's no conformal invariance physics or like an argument from physics that tell us that this should be some fraction. It's just a number. But in terms of beta, we are going to describe all our other quantities. So this is kind of our key number. So Xinyi and Daisuke went to improve the convergence in the scaling limit for the three-dimensional loop race random walk. Now that they had these results on the existence for the growth exponent, that allows you to know how you have to rescale your parametrization, so you can hope for convergence in the natural parametrization. So again, gamma m is a loop race random walk on our rescale, well, our ball of radius 1 that has this rescale lattice. And let's denote by Km the trace of this loop race random walk. So for now, we're just looking at the trace, but the idea is that we are going to give another parametrization. So it's actually that parametrization is defined by some measure. So our scaling factor should be of this order, m to the beta. But the way that things work are via these one-point functions. So you have your 1-point function, the probability that a given point, in this case, x hat always denotes a reference point that would be a half, 0, 0. So you just say, well, what is the probability that the loop race random walk passes through this point? And then when you look at xm hat, well, this one is the closest to x hat that actually lives on the rescale lattice. So if you have good estimates for this probability, then you can improve how close you're actually to m to the beta. With the bounds that we have given so far, well, this is up to taking logarithms and the quotient of that limit convergence. So that's the restriction over this result of 2018. How good are the 1-point function estimates? And then they define this measure that is, well, gives measure mass 1 to each point that appears on the trace, and then is rescaled by the inverse of this factor. So essentially, you're saying, well, I'm going to rescale by the probability that each one of these points belongs to my trace. And I'm going to take this random measure that is given by this curve. So the theorem is that if you look at this pair, the trace with this measure, mu_m, that converges to this limiting object k, and mu, that would be, so mu_m would be the occupation measure, and it converges to a limiting occupation measure mu. So one nice thing is that now you can say, then this gives me a parametrization of my path, so you can think that, so this convergence is in this topology where now the norm for two paths would be the following. Let's say that lambda I is a path, it's a finite path, so it is defined from 0 to its length t1, and lambda 2 has length t2. So the distance between two paths would be the difference between your lengths, plus now how far away are from each other. There is a lambda 2. So this will be the supremum of lambda 1 st1 minus lambda 2 st2. So here we are like going along our parameterized paths, and we are comparing how far away are from each other. So essentially, when are two paths close? When their lengths are close, and when I go along their parameterizations, those points are also close uniformly. So when you give these parameterizations, the ones defined by the occupation measure, then that's those paths parameterized by gamma u, mu, m, and mu, respectively, are close to each other. Good. So when were they able to have this factor fm is in terms of 1-point function, so one would aim to just have one number as a rescaling factor. And in this case, Xinyi and Daisuke had a strong 1-point estimates, but over dyadic scales. So if they were looking at the point along a dyadic subsequence, if set D is rescaled with along exponential scales 2 to the n, then they have a strong 1-point estimate. And this was actually important because the way that they prove this 1-point estimate is that they take advantage that when they are comparing one scale against the other, that they are exponential. This scale is growing exponentially. So that allows for better comparisons. Good, but our goal is then to improve this 1-point estimate so it doesn't have to only hold along dyadic scales, but for any subsequent, like from any x to the m where m is a real. So that's kind of, well, that's actually the content of this 1-point function estimates. So there are two versions. One is 1-point estimate when we look at the probability that one point is on this Km, it's on the trace of our loop race random walk on the sphere, on the unit sphere. And also this ball hitting probability. So now we look at the limiting object K, and we look what is the probability that it intersects a small ball around a point X. So that, I mean, X is in the unit ball. This Xm and X cannot be 0 and cannot be on the boundary. And this ball should be small enough so it lives inside our unit sphere. So we show that, well, in this case, the 1-point estimate, this this scales as m to the -3 minus beta, and times this function gx that depends on which point you are taking, and well, our error that decays polynomially. And a similar estimate for the ball hitting probability. And these constants, well, these functions gx that depend on who is the point that we are asking, what is the probability that this belongs to the loop race random walk or to its limit. Well, as expected, because of the rotational invariance of the limit, as G is also rotational invariant and continuous. So the way to go from ball hitting probabilities to the 1-point estimate is actually not difficult because we have this continuity result that essentially says, well, in the limit, if you know that you intersect a ball, let's say that this is a closed ball, centered around x of some small radius, then with probability 0, you are not going to intersect the interior. So essentially, this is the band that somehow the limit only touches the boundary of a ball. So this is saying, well, if you fix this ball, let's say around x of radius r, that is not going to happen. Like if you touch the boundary, k is also going to be inside. So then this allows to approximate the ball hitting probabilities with the 1-point estimate. And let me well, this can be a little bit technical, but let me tell you how you show something in between. So here I have Km, so this is the trace of the loop race random walk when the lattice is rescaled by 1/m. Now, well, this is on the discrete, but we are looking at the probability of hitting a ball around our reference point, half 0, 0. So the probability that this hits rescales by, well, depends on how, on the radius s to the 3 minus beta, and its error term. So essentially, we are looking at, we have here our unit sphere and this smaller sphere that is contained inside. Actually, this has to be smaller than half the distance to the origin and half the distance to the boundary. So S is small. And we are looking at the probability that we have something like this. This is a closer look, otherwise we cannot see. So we have loop race random walk that starts at 0 and goes through this ball. It doesn't have to pass through the center. It only has to go inside the ball and then live at some point in the boundary. This event can be described in a different way by looking at, let's say, our last exit from this small ball. So actually, it's more easy to think about this event as two random walks that start at y, and one continuous all the way to the boundary, avoiding the red ball, and the other one will touch 0 before leaving the unit ball. And this is related to escape probability. So something that I hide is that in many of the previous results, what the authors were estimating were not 1-point probabilities, but escape probabilities. And the thing is that these are interchangeable. Depending on the problem, sometimes it's, and for this model, it's easier to compute escape probabilities because we're talking about probability that 2 random walks do not touch each other and do whatever we want, instead of just 1 random walk that passes through a ball. Like, it's easier to think about this as 2 simple random walks that are independent. So this is what we do. Okay, so right now I'm only showing the loop ratios because it would be a little bit messy to think about the simple random walk as 1 and the simple random walk as 2. We would have like a larger subset, a lot of stuff intersecting with each other. But at the end of the day, what we want is to guarantee that whatever S1 and S2 do, they are going to, after loop ratios, they are going to give us the path that actually have the properties that we are interested in. So we have this kind of last exit point. So S2 is going forward, and essentially what we are asking is that it's not going to see this red ball anymore. But we also want that it's not going to erase whatever we get from S1. So originally we had a loop race random walk from 0 to the boundary, and now we are looking at this problem as 2 independent simple random walks, and we kind of want to glue together their loop ratios, but we don't want this S2 to interfere with S1. So the part that we are interested in is whatever happens with the loop ratio of S1 after it leaves this red ball. Because our condition is just to intersect inside the red ball, and whatever happens here, as long as there is some path that gets me from this would be the last exit. For going on the purple path, we are going backwards from Y to the origin. So here what we care is the last exit for the purple path up to 0. So we want that to survive. And we don't want the loop ratio of S1 to interfere. So then we are going to save this bit. Let's call it gamma hat. So this is the loop ratio of the simple random walk S1 between this last exit from the red ball up to 0. And then we want this blue path to avoid both the ball and gamma hat. What happens inside? Well, as long as, by definition, it's going to be connected. So it doesn't really matter if we keep this purple path or not. As long as we can go from Y to this other point, we're going to be OK. So we can write down this event, the probability that a loop race random walk intersects a ball, decomposing by these exit points Y, with the probability that this simple random walk S1 actually arrives to 0 before exiting. So this is this first event. Then my second simple random walk, sigma, avoids gamma hat, so it doesn't mess up with my loop ratios, is the second event. And then sigma avoids the ball. So then we are not happy because the distribution of all this depends on Y. So then the real work, so far this is just the setup, and it's very common to how you work with these 1-point estimates. Like translate the problem to escape probability, then try to like write down the event that you are interested in. But the real work is to show that you can compare this probability with a probability for any y on the boundary of the ball with a probability for a given point set. So up to an error, all these probabilities are comparable to a similar probability, and the price that you have to pay is changing these points U1 and U2. But there is some flexibility. I mean, this U2 was chosen as the first exit from the red ball, but there is the flexibility that inside the red ball, as long as we go from a point to another point, we are okay. So that's where you get 3 pages of comparisons. But at the end of the day, you just want to write down this, like this sum as just a comparison with some probability that is going to be for a fixed point. So then you can actually estimate this. So this is what I want to say, and you can go to the paper if you are interested in the actual like estimates. Let me finish talking now with the Minkowski content and how all this work, giving estimates for the 1-point function, actually gives you something nice about the geometry of our curve. So, the Minkowski content is defined generally for any bounded Borel set. In this case, we're interested in subsets of R3. And it's very simple. Like you take an enlargement of your set. So let's think about all the points that are at distance smaller or equal to R. So here it's my loop race run. Well, let's think about the scaling limit. Yes, we want the Minkowski content of the scaling limit. So this is K. And now we take an enlargement of K. So this looks a little bit larger. And then the alpha content of that subset A is this limit when, you take the volume of your enlargement and then you multiply it by this rescaling factor, R to the alpha minus 3. And of course, as it happens with these fractal measures, well, this is going to be trivial except for one value. That would be the Minkowski dimension or the box dimension. So what is our criterion for existence? And this has been used in a lot of works. People working with these criterions are Xinyi Li, Greg Lawler. They have do it for, well, of course, for the Schramm-Lohner evolution, also for cut points of Brownian motion and several other random objects. So essentially, you want to control these 2 quantities. One, well, our now well-known 1-point function, rescaled by, its exponent, and the 2-point functions. So I show you the results for 1-point function, but we can also control 2-point functions. Z and W are different, and when they are, you can say they are going to be far away at some scale, and then it's going to be, this 2-point function is almost, well, at least comparable to the 1-point function squared. So this is, that's where this 2 in front of the exponent comes from. So you need to show that these limits exist. You need to give bounds on them, and also you need to understand their rate of convergence. So, I mean, there are several conditions on the criterion, but these are essentially based on these 2 limits. So with our results, we are able to control those limits. So then the theorem says that if you have any nice enough box so that you don't get into any problem, then the beta Minkowski content exists. So you look at your limiting object, K, and inside this box, so the Minkowski content exists there. And then this Minkowski content defines a measure, and this is kind of what we were interested. At the end of the day, this measure induced by the Minkowski content is actually equal up to a constant factor to the limiting occupation measure that was obtained in the limit, almost surely. So this limiting occupation measure was an artifact that like appeared in the limit, but it wasn't too bad up to constant C0. So now that with these stronger one-point estimates and with the right way to parameterize the limiting object, we have our last version for the scaling limit of the three-dimensional loop race random walk. So we scale now just by beta to the m to the minus beta. So here you can think that you are rescaling the loop race random walk by this random measure, but this scaling factor is just m to the minus beta. And you get your loop race random walk, you parameterize by this measure, but at the end of the day, like this is a natural parameterization because you are going to like advance each edge on the same time. And then this loop race random walk now converges to a gamma, where gamma would be our limiting object k, parameterized by the Minkowski, beta Minkowski content. So this is very nice because we have used in the past the scaling limit for the three-dimensional loop race random walk to understand other scaling limits. So in this case, in work with Omer Angel, David Croydon, and Daisuke Shiraishi, we were looking at scaling limits of the three-dimensional uniform spanning tree, and we used the results for the loop race random walk. But those results were, well, restricted to, in the previous paper, but Xinyi and Daisuke, where it only worked for dyadic scales. So we had to work about, for the three-dimensional uniform spanning tree, we had to talk about scaling limits in plural, because we knew what was happening along dyadic scales, but because of the restriction from the loop race random walk, that was the extent. And now that we have this full result, this also improves this previous result for the uniform spanning tree. So now the convergence is full in this case again. And I think this is the end of the talk. Thank you. You can check the archive paper.